and welcome to 4.1. Chapter 4. We have been building over these first three chapters to Chapter 4. And after Chapter 4, everything is kind of just an application of this. Chapter 1 was basic training, where we learned prefixes, dimensional analysis, how to graph, relationships. Chapter 2 was representing motion. What happens when you move at a constant speed? How do you plot somebody's motion at constant speed? The chapter we just finished was acceleration. How do we handle if something's getting faster, getting slower? And now Chapter 4 is forces. What happens when you push or pull on somebody? And we're going to be talking about in Chapter 4 forces and how they affect motion. So the first thing we're going to talk about is what is a force? In simple terms, it's a push or pull on an object. If you push somebody or you pull something, and you can push or pull in a lot of different ways with a lot of different agents, we call them. Forces are vector quantities, meaning that the direction as well as the amount is important. Meaning, I can push on you with 100 pounds, or I can push on you with 200 pounds. And it depends how I push on you. Am I pushing you forwards? Am I pushing you backwards? Am I pushing you up? Am I pushing you down? Am I pushing you left? Am I pushing you right? So it's a vector quantity in that it's got a direction and a magnitude. Magnitude meaning how much, the amount. In the universe, when we talk about forces, like we can say you push on something, but when you boil down and you get to the bottom of forces, there are really only 4 of them in the universe right now. That's what we know, or we think that we know. 4 fundamental forces are gravity. You can push or pull on an object. Basically, you can pull on an object because they have mass. 2 things that have mass are going to naturally attract each other. We don't know why. We think we do, but we're not exactly sure. Magnets. You can use electromagnetism to attract or repel. And like when I push on you, we're actually using magnetism because I'm really not actually touching you. It's the electromagnetic repulsion of our electrons that don't allow them to go together. So when you push on something, or all the different forces that we're going to talk about really boil down to electromagnetism, that electrons repelling one another. And then these last 2 are inside of the atom. What keeps protons and neutrons together? There's some force that pulls them together. It's not gravity, because it's really hard to actually pull them apart. We've labeled it, it's called the strong nuclear force. The strong nuclear force is responsible for binding protons and neutrons. And the last one is the weak nuclear force. This is responsible, and you see this picture here, it's responsible for radioactive decay, like when you go from uranium down to thorium, and like when you're going through nuclear decay. We're not going to focus too much on these. We'll talk about gravity, but suffice to say, when we start talking about the different forces that we're going to deal with in this chapter, it really boils down to electromagnetism. Even though I'm going to say it's a push, there's friction, there's thrust, things like that. When we start talking about forces, we draw a lot of pictures. Inside of physics, we call it a free body diagram. A free body diagram is a picture. I just did a Google image search for forces, and there's a bunch of forces, and it labels what forces are on that object. For instance, here's a box that a person is pulling. So there's Ft, force of tension. So there's a rope that's pulling it. Fw, the force of weight. I will frequently call this the force of gravity. Gravity's pulling things down towards the center of the earth. They're probably having to oppose friction. So there's some friction between the box and the ground. So friction acts in the opposite direction of motion. So if you're pulling it forward, then friction's going to be pulling it back. And then there's this Fn, force normal. There's a supporting force provided by the ground that keeps it on the ground. So imagine if the ground just suddenly disappeared, this box would fall towards the center of the earth. A free body diagram is a picture. It's a drawing that includes forces acting on a system. So I'm going to do a couple of examples here. Number one, it says a flower pot falls freely from a windowsill. Here's a flower pot, and I like to draw my forces with red a lot of times. So then you label what forces are acting on it. And here's a common mistake that this is commonplace inside of physics. You know that gravity is pulling this thing towards the center of the earth. What a lot of people will do as they're beginning in physics is they put the arrow like that on the top. You should always draw your arrows coming from your object when drawing a free body diagram. So here's a free body diagram of a flower pot falling. Now it says ignoring any forces due to air resistance. If there were forces of air resistance, I could put them in. Maybe force of air resistance is really small. Maybe the force of air resistance is really big. It all kind of depends, and we'll get into the depends later on. But suffice to say for right now, they're just saying to ignore that, so we're going to take it out. Number two. A skydiver falls downward through the air at a constant velocity. It says the air exerts an upward force on the person. So here's my skydiver. And then we'll draw the forces. When you're making a free body diagram, this is a force that will always be there. There is no place in the entire universe that you can go to escape gravity. Gravity is just an attractive force between two objects that have mass. And since there's mass elsewhere in the universe, there's always going to be gravity. So on Earth, gravity pulls straight towards the center of the Earth. And so on all my free body diagrams, you're going to notice I've got gravity. And then it says they're falling down at a constant velocity. To me, this actually means something. It's going to mean something more to you as we get further on through this chapter. But I know that the force of air resistance is the exact same size as gravity. That's why they're moving at a constant velocity. If it said they were accelerating, then I know that the force of air resistance is smaller than gravity. But for right now, don't worry about it. We'll get there. Number three. A cable pulls a crate at a constant speed across the horizontal surface. So here's my crate. And now I'm going to draw my forces. Again, the one force that's always there. The force of gravity. Now, there's a cable that pulls it. And you can just write force of C, force of cable. Or you can write out cable. Or maybe you saw it before in that one that I showed you, force of tension. Like any rope that pulls on something, we call that a tensile force. So, it says the surface provides a force that resists the crate's motion. So there's something that prevents the crate from sliding. And you guessed it. It's friction, force of friction, F sub F. Now, there's always, when you're on the ground, and only when you're on the ground, you'll notice in numbers 1 and 2, there was not this force. When you're on the ground, there's a supporting force provided by the ground. Like me standing here right now, if the ground suddenly disappeared, I would start accelerating towards the center of the earth. The ground is actually pushing against me, and we call that the normal force. Normal. It's an English word that means perpendicular. The normal force is always going to be perpendicular to the surface. Number 4, a rope lifts a bucket at a constant speed. So here's my bucket. And there's a rope that lifts it. So again, the one force that you're always going to have, gravity. Now my rope is lifting it at a constant speed. Again, that says something to me. When you're going at a constant speed, the force of the rope is the same size as the force of gravity. If this that said, if you're accelerating, then one of these forces is bigger than the other. We're going to get to that. But I wanted to kind of introduce that idea to you right now as we're going through it. What happens if you combine a bunch of forces? Like, what if you have a whole bunch of forces acting on something? Like, you got a person here, another person here, and then you got another person here. We have two forces. You have something pulling from the left and something pulling from the right. Now, you let these things go, the left one wins, and what we have is a net force. So what I'm going to do, like maybe let's say this person pulled with 60 pounds. Maybe this person pulls with 20 pounds. This person over here, maybe they pull with 10 pounds. So the net force is the sum of all the forces. The net force in this case is going to be 60 plus, well, first of all, I got to define which direction do I want to be positive. I'm going to make to the left positive, so that would be a positive 60 plus, and it's a positive 20, and that's a negative 10. You could think of it as 60 plus 20 minus 10, but 60 plus 20 is 80. 80 minus 10 is 70. So this net force equals 70 pounds. Now, I could have done this problem making positive the other direction. And then this would be a positive 10. And it would have been a negative 20. And it would have been a negative 60. And you add these together and you get negative 70. And what that means is that my net force is in the negative direction. And the negative direction is this way. So it's no matter what way you decide is positive or negative, the net force is going to be in the same direction. If I make to the left positive, oh, I get a positive 70. If I make to the right positive, oh, then I get a negative 70. In both cases, the net force is in this direction. And it's equal to 70 pounds. The net force, when we do these things, is just the sum of all the forces acting on a body. So when you go over here, we'll put that in. The net force is the sum of all the forces acting on a body. And in sum, you add them up. We should probably add direction is important. Some forces can be negative, as you saw in my example. The net force can also be 0. You know, if I go back here and I set this up so I have equal people here, and then I run this, these people are pulling against each other and you have no motion, right? The net force equals 0 in this case. Here's an example. The net force on this would be 0. The net force on this would be 200 newtons to the right. And the net force on this case would be 100 newtons to the left. Newtons is a unit of force in the metric system. You know, I introduced to you pounds before, but in the metric system, a newton and a pound are roughly the same idea. Newtons is 1 pound.
1 pound force is equivalent to 4.448 newtons.
So 1 pound is equal to 4.448 newtons. Or, yeah, that's for right now. That's all you need to know, that 1 pound is equal to 4.448 newtons. We're going to talk now about Isaac Newton, and he came up with laws that relate to forces. And you just saw the first one. Newton has 3 laws: first law, second law, third law. His first law is objects in motion stay in motion in a straight line unless acted upon by another force. Objects in motion stay in motion in a straight line unless acted upon by another force. Here I've got an example of that right here. This is Chris Hadfield when he was on the International Space Station. Really good example of this.
Just like this.
He's eating dinner, and he's showing how he makes a peanut butter and jelly sandwich.
18 months.
But you'll
So
see
what we're
this
gonna do
idea
is
coming
we're
up
gonna
here.
open up our
Objects in
tortilla.
motion stay in motion in a straight line. And you'll see it with this jar of honey right here. Watch after he lets go of it.
And we will have
See how this is moving in a perfectly straight line?
open up the tortilla.
Up on the International Space Station, they're falling at the same rate that gravity would have them fall, but they're just going forward so fast that they're falling together. So it seems as though there's no gravity there. Even though there's plenty of gravity there, there just seems to be no gravity. But you can see when he lets go of this honey, objects in motion are staying in motion in a perfectly straight line. Look at that perfect straight line that thing's moving in. Now, on Earth, things don't move in a perfect straight line. Right? You let go of something on Earth, Earth starts attracting it right away, so it gets bent towards Earth. And you can see that with Giannis taking a three-point shot right there. Objects in motion stay in motion in a straight line unless acted on by another force. The reason that basketball wasn't going in a straight line is because of gravity. Right? Gravity is the force that keeps that off of that straight line. Objects in motion will stay in motion. The reason that things don't stay in motion on planet Earth is because there's air resistance and there's friction. If there was no air resistance and there was no friction and there was no gravity, like out in space, no air resistance, you let go of something and it moves in a perfectly straight line for eternity. Newton's second law, it says this. It says that an object's acceleration is directly proportional to the force acting on it. Directly proportional. Like if you increase the force on something, you're going to increase the acceleration. You decrease the force, you decrease the acceleration. And the object's acceleration is inversely proportional to its mass. Meaning if you got a big mass, hard to accelerate. Small mass, easy to accelerate. It boils down to this equation, F equals ma. In words, it says, an object's acceleration is directly proportional to its force, but indirectly proportional to its mass. Let me show an example of that. Here's two tennis balls that are rugged into an air compressor. One of them is really heavy and one of them is really light. They're the exact same size, but I think that the yellow one is really light compared to the red one.
We're going to go 3, 2, 1, and...
And you can see right there, the same amount of force is acting on them, but that yellow one goes way farther. Here's another example kind of in the motorsports world. There are two cars here. One of them is a Volkswagen, and the other one is this like racer. They have the exact same engine in them. So that engine is able to provide the exact same amount of force. But because one of these weighs literally half of what the other one does, an object, its acceleration is indirectly proportional to its mass. Small mass, easy to accelerate, and you can see that in this race right here. We call this in the motorsports world power to weight ratio. How much power, force, how much weight do you have? Mass. Newton's third law says, you probably have heard of it. Every action has an equal and opposite reaction. Every action has an equal and opposite reaction. And I could say this, every action force has an equal and opposite reaction force. Here's an example. This person has rigged up like a mousetrap that's going to fire this projectile. When you push the projectile to the right projectile pushes you to the reverse. And this is the exact same thing as when you fire any firearm. Like when you when you push on the bullet pushes on you. So these guns are really, this is an elephant gun. They shoot elephants, sadly. But this is the size of the projectile that they're shooting. When your gun pushes on that pushes on you. And this is the exact same thing that's taken us to the moon. Here's an example of the space shuttle launching back in the, I think, 2000s. This is like 2003, something like that. But it's really cool. It really shows.
24 frames, so it's about 1/16 of
like how mass is ejected. This is a time code over on the right, and these are seconds right here. So this is
absolutely gorgeous today.
When this 12 goes to a 13, that's 1 second elapsing.
So in the film industry, they call this magic hour, and there's no question about it that this is one of the best times of day to take photographs of the shuttle. You have these rich colors and just a beautiful blue sky to sort of highlight all of this. So I find these pictures.
So here, 1 second is
second
elapsed.
to none in all of the launch imagery that's been taken. I should say that these boosters shed about 10,000 pounds of mass per second once they're lit up, and that's each. So it's
That's amazing. This thing is pushing out every second 10,000 pounds of material. That's a lot. Like 1001, 1002. Every second, both of these are shedding 20,000 pounds. So imagine an elephant gun pointed down that's shooting 20,000 pounds of material at the velocity. You're going to have a reaction force which drives this thing up in the air. And that's how thrust actually works. Every action, pushing that gas out the back, has an equal and opposite reaction, pushing you away from it. These are some of the forces that we're going to see throughout this chapter. And the rest of physics, in fact. Friction is a very common one. It's always opposite the direction of motion. The normal force, it's a force provided by a surface, and it's always perpendicular to and away from the center of Earth. A spring force, so like if you stretch a spring, it's a restoring force. So spring, like if you compress it, the force is opposite. If you stretch a spring, the force pulls you back. So it's a restoring force, they sometimes call. Tension, that's a rope. If you hook something with a rope and you pull it or you lift it, that's always in the direction of the rope. The thrust force, you just saw in a rocket, it's in the same direction as the acceleration. And then the last one is weight. Weight is an attractive force provided by Earth pulling us down. And that's where I want to leave us today, is the difference between weight and mass. There's a difference between weight and mass. I have here a calculator that talks about our weight on different planets. So Mr. Hare, currently weighing 185 pounds, it will tell me how much I weigh on each of these planets. Now, my weight is dictated by how massive the planet is. Mercury has less mass than Earth, so 185-pound Mr. Hare only weighs 70 pounds. But Jupiter has much more mass than Earth, and so 185-pound Mr. Hare is going to be 437 pounds. And you can see Saturn, I weigh a little more. Uranus, a little bit less. Even though Uranus is really big, it doesn't have a lot of mass there. Neptune, and then Pluto. I only weigh 12 pounds on Pluto. Imagine me on the surface jumping with my same ability, but only weighing 12 pounds. I probably could set the high jump record on Earth pretty easily. Some other ones, these are the Sun. This will be at my weight on the Sun. Over here, this is a good one, a neutron star. Neutron stars are collapsed stars, so they're just a star that's it's in the size of maybe New York City. So take something the size of New York City, but you take a lot of mass, and Mr. Hare weighs quite a bit on the surface of a neutron star. I would not get close to that before. I would spaghettify. That's actually the technical term. When you get close, it would pull on your feet a lot harder than your head, and it would actually just pull you apart. So mass. Your mass is the same everywhere. It's in kilograms. My mass on Earth is the exact same as my mass on the moon. It's the exact same as my mass on that neutron star as well. It's kilograms. My weight is different. My weight is different. It's different everywhere, and it depends on what planet. And even where on the planet I'm located. Pounds and newtons. And we'll talk about how to find a newton and what that means in the chapters to come. So, thanks for hanging in there. Welcome to Forces.